So, we are talking about facilitated diffusion of proteins on DNA. Right. This is the 2013 JPCB paper. And just to brief recap of what was the setup of the problem. So, I have a DNA of L base pairs 1, 2, 3 all the way up to L minus 1 and L, right. I have my protein molecule which needs to find a particular target site, some particular target site on this DNA, which I call as some NF, right. So, this is my protein. The proteins, if it is bound on the DNA non-specifically, it can do random walk along the backbone with rates u, but it can also come off to solution with a rate k off, and it can bind back on with a rate k on. And when it binds back on, it binds back to any site with equal probability. So, there is no memory of where it unbound from. And I think that's about all the rates. And then we are interested in how long does it take for the protein to find this target site. Right. So, right. So, hopefully this part there was no doubts, right. This was the setup of the problem. U k off k on. And then initially we started out by writing the forward master. So, let me just have that as well. And let me have that equation over here. So, del P in general, the forward master equation del P del T of at xi t starting from some xi naught t naught, right, is an integral over all possible intermediates times the gain term. So, P, so let me write a transition rate from this intermediate site to xi, and then the probability that you were at that intermediate site having started from wherever you started out from, minus the loss term, which is that you were at this site having started out from xi naught t naught, and then from that site you go to any other, whatever are your allowed intermediate sites, right. So, integrated out over all possible values of this intermediate site xi prime, right. So, this was my forward master. And then in this context where I said that, well, this in the short form notation that I had was my Pn of t denoted the probability that I was at site n at time t, having started from some, I don't know what I called it, n naught, I think at n naught probably at some time t naught. So, this was my Pn that I am going to write down the equation for. And for this, if I write down this equation, d Pn t dt, right. So, this psi prime now means, so the states that I could have come into psi n from are my two neighbors n minus 1, n plus 1, and of course, the solution. This is my solution, which I had called the state m. So, m. So, this integral over psi prime in this particular case means that I have to sum over these states n minus 1, n plus 1 and solution, and then I will have the corresponding rates for that. So, u times p n minus 1 of t plus u times p n plus 1 of t plus k on by L, because k1 was the total rate, p m of t, right. So, these are my incoming terms, and then I have my outgoing terms. So, if I was at p n of t, I could have gone out to these three sites. So U plus K off. Right. So this was my forward master equation. This is what we had, I think, written down the last day. And for the edge, we had written down for the edge sites as well, P1, PL, and the solution. I'm not writing down again, but you'll just have to see essentially from what states could you have come into this state that you desire, this nth state. If you are at this boundary 1 or L, you can only have come from 2 and the solution, or L minus 1 and the solution, and therefore that will affect what terms you have over here. Okay, so this was the forward master. Fine. So now I want to write down the backward master equation. And hence, essentially, what I want instead of Pn, I want this Fn of t, Fn of t, where this is the distribution of first passage times, where this is the distribution of first passage times, having started from site n. At t0, right? Or if you prefer, I can call this n naught. Okay. Because remember, when I'm writing down the backward, I talk in terms of the initial site, the starting position, which is n naught in this case. And again, so if I'm writing down the backward master equation, so del p xi t in general, of course, del p xi t having started from xi naught t naught del t is an integral over all possible intermediates of p of something, your transition rate from the initial state to whatever intermediate site that you have, right? And then from that intermediate site, xi at t, from that intermediate site t naught, right? And then minus the same rate, so p of something minus the same rate, omega of xi naught to xi prime, and then xi t, xi naught t naught, right? And again, this came from the term that in the initial time you made a hop to this state xi prime, and then from that xi prime you're going to xi. This came from the term that in the initial time you did not make a jump from xi naught to xi prime, and therefore in the remaining time you have to go from that xi naught to the final state. Okay. So unlike if you compare the forward master to the backward master, here the transition rates are reversed. So xi prime to xi and xi to xi prime. Again, note that here both of these rates are the same. It's xi naught to xi prime here, xi naught to xi prime here as well. Right? The probabilities are different, of course. And here, this xi prime is all states that you could have gone to from this initial state. Right? So whatever are the accessible states from this initial state. Yes. Which one? You mean in one of this? Huh? Yes. So that's what we had done earlier, right? That so this was in that time delta t. Then this was from t naught plus delta t to t. But then we had done the Taylor series expansion, and then we had cancelled the terms, and then we had obtained come here. But originally, yes, that's what we had started out from. So that is why, this term is not exactly what is the remaining probability. Things have gotten cancelled and so on, because remaining probability was 1 minus omega and then times p and so on. So this is the final form after we had done all those small delta t expansions. And here it is indeed a t naught. And then we said that, of course, if this is my backward master equation that is obeyed by the probability, it is obeyed by the survival as well as the first passage distribution of first passage times as well, right? And remember, my survival probability of the fact that you have not reached the final state up till time tau, final state being xi f, having started from some initial state psi t, was this integral p of xi prime t xi naught t naught integrated over xi prime, right? And we showed that if you am talking about the first passage, then the distribution of first passage times f of tau, again to reach xi f having started from xi naught, is the negative derivative of the survival. So, and then we showed that if this is my backward master that is obeyed by the probability, is the same equation that is obeyed by the survival. It is the same equation that is obeyed by the survival probability as well as by the first passage. So, you, for P you could write S or you could write F. Again, for P you could write S or F. So, here we are of course going to write down the distribution for this first passage times Fn. Therefore, we will write this in the form of the backward master equation. So, what I want to write is d f n naught of t dt. Right. So, I am starting from n naught. I want to reach some final site nf. What is the distribution of those times fn of t, where it reaches for the first time. So, it has started from n naught, and what I need to integrate out over are the sites that it could have accessed from that initial state, right, n0. So, what are those sites? So, if it started from n0, where could it have gone in the next instant of time delta t? Huh? n0 plus 1, n0 minus 1, and m. Correct. So, this is the states that I need to sum over. So, therefore, what I will have is u of f n0 plus 1 of t plus u of f n0 minus 1 of t plus k of m, sorry, not m, fm fm of t, right, minus what? Minus huh? This should be k on. Why should it be k on? Huh? Remember, the backward master equation has no gain loss interpretation. That is for the forward master. Here I am thinking about, I have started from some site n or whatever, n0, I call this n0. I can go to n0 plus 1, n0 minus 1, or I could come to m. These are my three processes. So, to come from n0 to m, what is the rate? It is an unbinding event. So, the rate is k off, not k on, right. So, it is a common mistake in that sense, because the gain loss interpretation, like I say, for the forward master is more natural. All right, right. Now, minus what? Somebody? Rohit, minus what? F of what? Which f will come here? F of n naught. Okay, f of n naught of t, fine, let us see. And what rates will come here? U plus another u and k on. Everybody understands? Everybody agrees? Huh? He disagrees. He says k off. Anyone else? Which one, Shomo? Shujit, which one? Why not? It is written, right? It is written in the above line. This is my structure of the backward master equation. And I have told you what states to sum over. So, K off. It's the same omega xi prime xi naught that is appearing on this term versus on this term. So, whatever rates you have, u K off is the same rates that is coming here, u K off. Okay. Again, here the rates are flipped. One is xi to xi prime, and therefore, in one case you have K on, in another case you have K off. There, the rates are actually the omega that comes is the same transition rate. So, you have the same rates u K off, u K off. This is of course for all bulk sites. Is this clear? Because this is tricky. Writing down the backward master equation sometimes by default we try to think about the forward. So, it's a little gets used to, takes some getting used to. L minus 1, right, up till here. All right. So, now edge sites. So, let us see d f1 t dt. So, this means that you have started out from site 1, you are reaching the same target site NF, and what is the distribution of times? So, what will this be? Yes, someone? U into F2 plus what else? Plus K of Fm, and then minus F1 of t. Very good. Right. Similarly, of course, for Fl of t, again you have two things, u of Fl minus 1 of t plus K of Fm of t minus Fl of t u plus K of. And then finally, what is left is the solution side. So, it's looks weird because in these equations, it makes sense somehow intuitively that one term has a K off, the other term has a K on. In these equations that I've written, all terms are K off. So therefore, all the K on terms will be where? It will only be in the solution equation. So dFm dt, dFm t dt. All right. So if you are, so now the thing is that your initial site, your starting point is in solution, your protein starts in solution, and therefore what is the first step that it can take out of that? So what F's will come here? What will come here? Just K on, because I defined this as K on by L, the binding per site. So K on, sum over of all Fj of t, j equal to 1 to L, right? Because from the solution you can go and bind to any one of these sites. And then what else will come? So that is the first term. What is the minus term? Minus K on Fm of t, right? So here both terms are K on. Well, actually, since I have this summation, I should write K on by L, because the L will come from this L summation. So it's K on by L, because the total rate is K on. All right. So these are my set of backward equations that I now have. Okay. Writing this down is the first, the most important step. Now, of course, comes how to solve this, but before we do that, is this clear? Is this backward equation versus the forward equation clear? Okay. So again, whenever you're writing forward, think in terms of the final state, and where can you get to? How can you get to the final state in one step? If you're writing down the forward equation, think in terms of the initial state, and how can you escape that initial state? I mean, whatever you want to find. So, in this case, I have a target in this protein search problem, and I want to find the time when it reaches this target for the first time. But in any process, so if you are talking of time, it means time to something, right? Time for something to have happened. So, whatever is that something to have happened, that is your final state. No, so like I said, so this f n naught of t, f n naught of t is essentially the distribution of times f of t to reach the final state having started from n naught. So, that is what is I am calling. So, I have suppressed this nf, but it is the same nf essentially, right. So, that is what exactly like I had suppressed over there. So, this is what f n naught means, that how long does it take to reach nf having started from n naught at time t naught, if you, but this is the time gap, so it does not matter in time interval t. So, that is the interpretation. So, you should practice writing down backward master equations. You know, there are a bunch of papers which write them down. Takes a little bit of getting used. So, yes. Why do I divide by L? So, that is the way I have defined my rates, that my total, so my binding rate per site. So, it can go and bind to any site. At every site, I have a rate k on by L. So, that my total binding rate that I was in solution, now I have gone and bound to the DNA, that total rate is k on. If I said that each site it was k on, then my total rate would have been L k on. It is just a nomenclature, whichever way I want. That I could have called as some k on prime. So, it is just the way these people have defined essentially. All right. Okay. So, now I will solve this. The solution is messy. The solutions often are. So, I will probably not work it out in full detail, but you can look at the paper. Anyway, so what they do is again this paper, right, 2013 JPCB, Kolomaisky, Wechsler, Kolomaisky. So, what they do is they work in Laplace space. So, you define the Laplace transform Fn tilde of S is equal to integral dt Fn of t e to the power of minus st, okay. 0 to infinity. Right. And then you do the Laplace transform of these equations, each of these equations, and of course, you need a initial condition. So, the initial condition is that if you start at any site which is not nf, then at t equal to 0, you have probability 0 to have reached the target, right. So, let me just say n naught, since I am saying n naught. Sometimes if I forget the n naught, just imagine it is n naught. Okay. So, as long as you do not start from this target site itself, the probability that you have reached in time 0 is 0. So, you have to make some steps. Okay. So, now you do this, take Laplace transform of both sides of this equation, right. So, the idea is to transform this into a set of algebraic equations so that you can then solve. So, what is the Laplace transform of a derivative? S f tilde. So, I am doing f n naught. So, f n naught of S, then minus, okay. So, which is 0. So, I will just not write that term, right. So, S m f n naught of S is equal to whatever u. So, let me just do it instead of writing step by step. So, here I also have a f n naught tilde of S, so which has a 2u plus k off, and I have a S on the left hand side. This has a minus sign, which means that if I bring everything together, I will get over here S plus 2u plus k off of f n naught tilde of S, right, is equal to this thing u f n naught plus 1 tilde plus u f n naught minus 1 tilde of s plus k of fm of s. And similarly for these ones, you will get, instead of 2u, you will get s plus u plus k of f either 1 or L, whichever, tilde of s is equal to u f 2 or L minus 1, either 2 or L minus 1 tilde plus k of f m tilde of s. Right. And then for the solution, you have a k on there, and you will have a s here. So s plus k on. So s plus k on f m tilde of s is equal to k on by L is equal to k on by L sum over f j tilde of s, j equal to 1 to. So I had these differential equations. I take the Laplace transform. I transform it into a set of algebraic equations. I have L plus 1 unknowns. I have L plus 1 equations. So here I have, these are for all 2 to L minus 1. So I have L plus 1 equations and L plus 1 unknowns, which are these f tildes. So in principle, I can solve them. I can write down what are these f tildes, right? Correct, of course. So f of nf, right? So it's fine. So if you start there, you will get immediately absorbed, which means essentially your f of nf tilde of s is delta t e to the power of minus st, which means this is just 1. Okay, so that's, thank you. You'll need that one as well. All right. So it turns out what these people did was they tried out a trial solution, which was a polynomial solution. Fn tilde of s was a y of s to the power of n plus b. So I'll not do this. It's too long. So they try out a polynomial solution, and you can substitute that into this equation and see that when does it satisfy this equation. But ultimately, at the end of the day, you can solve this Fn tilde, you can solve this set of algebraic equations. So I'll just write down the final solution. It's not very pretty, but it has a closed form analytic solution, which is, let me write, 1 minus b y to the power of n plus y to the power of 1 minus n by y to the power of nf plus y to the power of 1 minus nf and 1 minus b y to the power of n minus l plus y to the power of 1 minus n plus l y to the power of nf minus l plus y to the power plus l. So this is when the initial site is to the left of the target, and nf, and this is when the initial site is to the right of the target. And then of course you have it if it is in solution, and in solution I'll write down what these y's and so on are. So if you are in solution, it is k on by k of plus s gamma of s. Even writing down the solution takes so much time. Ls so this is for n equal to m. So you can solve this set of equations regardless of where it starts out from, and this. Yes, because it has to have continuity. So in both of these equations, if you put nf n equal to nf, then you will get 1. So it's a consist. So you put it here, doesn't matter, you will get 1. So I have bunch of unknowns over here. Y of s is s plus 2u plus k of plus minus square root of that thing, s plus 2u plus k of whole square minus 4u square by 2u. Sorry, not plus minus, minus by 2u. B is k of by k of plus s. There's no need to copy these. I'm just writing for the sake of completeness. And f of s and gamma of s is something is y by 1 plus y. Sorry. So anyway, it's complicated, but you can solve it. If you spend half an hour, 40 minutes just looking at these equations and then working through the steps, all of you can solve it. You can look at the paper, even the paper doesn't do it in great detail, but anyway, if you get stuck and you are not able to get to the final solution, you let me know. I have detailed notes which works it out. I just don't want to waste time going through all the steps. But in principle, therefore, you can find your Fn tildes. Okay? And therefore, of course, you can do the inverse Laplace transform and you can find out what are these Fn of t's, Fn naught of t's. These are all n naughts. Huh? I keep forgetting the n naught. But what are these Fn naught of t's? So what is the distribution of first passage times for any step that any state that you started out from? And in particular, of course, if you're interested in the mean first passage time, so if you're interested in the mean first passage time starting from some specific site m, tau of m, right? That is, of course, d tau, tau, f tau, fm tau, right? From 0 to infinity. That's the first moment, the mean. If you have the full distribution, tau f tau, starting from that site, that will give you the mean time. And like we had discussed, you can get these. You don't need to, if you're interested in the mean times, you don't need to always do the inverse Laplace transform, because this you can write as a derivative of these Laplace transforms. So this is 0 to infinity d tau, right? dds, right, of fm tau e to the power of minus s tau minus derivative, right? So this is therefore, because that will bring down a tau, which is what you want. So therefore, these are nothing but, and this thing is nothing but your Laplace transform. So this is nothing but the first derivative of your Laplace transform of this Fm tilde of S. Okay, and then of course you have to put S equal to 0, taken at S equal to 0. Right. So if you're interested in the, if you can do the inverse Laplace transform, well and good. Of course, not always possible given that the expression itself is so horrible. So if you're just interested in some of the moments, the first few moments, instead of doing the inverse Laplace transform, you can take the derivatives, the first few derivatives of the Laplace transform to get what are the moments. Okay. So in particular, I will just write down one. So if I write down the mean time it takes to find this target NF, starting from the solution, let us say. Okay. So let's say you have a protein in solution, and you want to say what is the, you have the full distribution of times, of course, because that is your comes from the inverse Laplace transform of this, the Fm. But if you're just interested in the mean time, on an average, how long does it take? So average tau starting from solution, capital M over here. So you take the derivative of this expression with respect to S, and then at the end set S equal to 0, you will get that mean time. And I will again write down the final expression, 1 by k on L by gamma of 0 plus 1 by k off L minus gamma 0 by gamma of 0. Okay. Where gamma is written somewhere over here. Gamma of S equal to 0 means you have to put S equal to 0 in all of these y terms and get what that means. And if you plot this, so this is the average time that it takes to find this target NF. And if you plot this, so what are your variables over here? Your variables are of course your hopping rates U, your dissociation rate and your association rate k on and k off. Okay. So in particular, if you fix one of this, let's say you fixed your association rate k on, and you vary these in this manner. So people define what is called as a scanning length U by k off. Okay, and then you plot this average time taken to find the target. Okay. So this expression as a function of this variable U by k off. Okay. Why U by k off? What this says is that essentially if your U is high, right, you have large U as compared to your k off. That means you're going to do 1D random walk for a long time before you come off, right. So higher values of this side is when you're doing a pure 1D random walk, right. On the other hand, if k off is very high as compared to U, then you hop a little bit, maybe 1 or 2 sides, but then you come off, right. And in the limiting case, when this is very, very high, you essentially bind somewhere. If that is the target, well and good, otherwise you unbind, right. So this side is your pure 3D diffusion, essentially, right. You bind somewhere, if it's the target, good, otherwise you immediately unbind, bind somewhere else, right. That's your pure 3D strategy. Okay. And somewhere in between is this facilitated diffusion, where you do a 1D for some time, for some finite length, which is the scanning length, this is a length scale, and then you unbind and do 3D diffusion and again rebind. And if you plot this, so, you can go to Mathematica and put this horrible expression and so on. You'll find that what it looks like is something like this. So in both of these limits, when you do a pure 3D search versus if you do a pure 1D search, your times are higher as compared to if you do a combination of these two, where you do a 1D search for some time and then you unbind and then you again start searching. Okay. So this is the central idea of facilitated diffusion, and it turns out, at least in some cases, again this is not proved, but it turns out in some cases, especially in prokaryotes and bacteria, if you put in the numbers for 3D diffusion coefficients and 1D diffusion coefficients into this formula, then this sort of reduction that you get, sort of these times that you get, in this regime, when you have facilitated diffusion, allows you to sort of search for targets within biological timescales, so which you could not have done if you were doing a pure 1D search or a pure 3D search. Okay, so that's the idea of facilitated diffusion. So I'll stop here. There's a bunch of papers, like I said, on this. It's something that was proposed way back in the late 80s, I think, by Berg and von Hippel and company. Berg, there were a bunch of classic papers, and someone else also. Sometime in the 1980s when this idea was first proposed. And then there's been many things done, including this full sort of analytic formalism. But you can take now, you can introduce more and more complexity into the problem. You can say that there are already some sites where proteins are bound. Then what happens? You can say that this unbinding probability is not agnostic to where you. This rebinding probability is not agnostic to where you unbound from. Maybe it depends from the site that you unbound from, and so on. So you can do various sort of improvements to this basic idea. But the basic idea remains this: that you need some sort pure 1D or pure 3D is not good enough. You need some sort of a mixture of these two in order to find search for targets on DNA. Okay. Yes. What is that? This is, I assume, a polynomial solution, and I substitute it in those equations, and I see for what values of A and B I can solve it. A is basically, so A I have written in terms of B itself. Yeah. So in this, this is, you put this and you solve for A and B, but essentially in this, which is my final answer, I have no more A. So I've solved for A over here, and I substituted that. It's in, I've written it in terms of B, essentially. It's 1 minus B, I think. Huh? If I substitute n equal to nf, is it not giving? I think I have what is it giving? Nf 1 minus nf. One, because I've forgotten this b. Sorry. Yeah, there is this plus b over here. Thank you. Which one? This one? Check. I don't know. I don't have it here, but you can check whether this satisfies. Here definitely, because I have to get one. Okay, so I'll do. Is this fine? If not, you want to ask something, please ask. Else I'll do one more problem, one more example. So this says that I have started from solution. How long does it take me on an average to find this site? Depending on what strategy I employ. So this x-axis is essentially different strategies. I do a pure 1D search, that is one strategy. I do a pure 3D search, that is another strategy, or I do a mixture of these two. And then what this says is essentially that if I do a mixture of these two, I can get a reduction in the time, average time that it takes for me to find the target. Here in this regime, the time taken to find the target is minimized, and it turns out if you put the numbers in, this time is a realistic sort of time, and therefore the assumption is that proteins must be doing something like this in order to locate targets. So, because the simple back of the envelope calculation that you do, if you put a pure 1D diffusion coefficient, and like we said, right, it goes as L square by D, your time, tau 1D goes as L square by D1. That gives you something which is unphysically high. So this cannot be the strategy. Even pure 3D, if you put instead of D1, you put D3, that also cannot be the time. So something else, and this is one of the leading candidates that is out there. Which one? The extreme right, because when is lambda going to infinity? When your k off is essentially 0. So once you're bound, you stay bound all the time. So you just hop. You just hop along the DNA backbone. So therefore it's 1D. Huh? Sorry, say that once more. Huh. So here, of course, if your k off is very high, so lambda is equal to 0. So either u is low or k off is high. If k of is very high, what does that mean as compared to you? That you bind somewhere, before you can hop, you unbind because your k of is very high, which means that what your search strategy is bind somewhere. If it's not the target, you again unbind because k of is high. You again bind somewhere, you unbind. You again bind, unbind. Ultimately, if you bind to the right side, then it's fine. Then you have found your target. So that is your pure 3D essentially. Again, remember this 3D is a toy 3D in that you are unbinding and then rebinding with complete no memory essentially of where you unbound from. But up to that, this is like the pure 3D limit where you are just so this is called the jumping regime, where you just jump from from solution to a site, and if it's the correct site, stay there. Okay. Anybody else? Else I'll do. I have 2 more examples, but I think I can only do one. I'll just do one. This is a simpler example in that I will not write down the full backward equation, but I'll just work with the mean times. And this is in fact the paper that I gave in the assignment and also the mid-sem. This cooperative cargo transport by molecular motors. So this is PNAS 2005. Cargo transport by molecular motors. So again, just to remind you of what was the setup of this and remind myself of what was the setup of this. So here I had a microtubule or whatever, some cytoskeletal filament, microtubule, actin, whatever I have. Okay. And I have a cargo. Remember, a cargo is something like a vesicle inside cells, perhaps, or organelle, which needs to be transported from one point to another, and it does it by walking on these tracks, which are, again, if you remember, these polar filaments, structurally polar filaments, either microtubules or actin, right? And then you have this cellular cargo, and how the cargo gets transported is that there are molecular motors which bind to the cargo and also to the filament, right? And by expending energy, so they take in ATP and they convert that chemical energy into mechanical work. They take steps, these molecular motors take steps on this filament, and as they take steps on the filament, they drag the cargo along with them. So this is now the new position of the cargo, right? Cargo prime, and so on and so forth, right? So as these walk on the microtubule filament, or the actin filament, whatever, the cytoskeletal filament, it sort of transports the cargo. And essentially, how much can this cargo gets transported in this manner, right? So you can ask that, well, this is the mechanism that I have molecular motors, and in principle many molecular motors. So many molecular motors. And this molecular motors attach the cargo to this biofilament, the cytoskeletal filament, and then they walk along this filament in a particular direction, or maybe in both directions if you have multiple types of motors, doesn't matter. I would want to know essentially how long does this cargo stay bound to the filament, right? Because that will tell me how much typically has it moved. Okay. So one of the questions that you could ask is that how long does this cargo stay bound to the filament? And the moment I have posed a question like this is a question about times, right? This is a question about how long, so this is a question about times, and therefore all of this machinery that we've been doing is something that would be appropriate to answer this question. Okay, is this, again, is the biological question clear? Now let me see, what had they defined in this one at least? So this 2005 paper again. So the idea was that at least assumptions was that this cargo came decorated with capital N number of motors. Sorry. So So in general also this is true. When you have cellular cargo, you have motors decorating the entirety of the cargo essentially. Okay. Some density of motors, whatever. But the A over here is that you have n molecular motors like kinesins, dyneins, myosin. Remember, we have talked about molecular motors as well, attached to cargo. Attached to cargo. Okay. These are always attached to the cargo, but they are not necessarily always attached to the microtubule, right? Because in order to walk on the microtubule or actin, whatever, in order to walk on the filament, the motors need to bind and unbind, right? So a bound state of the cargo is when you have at least one of these motors attached to the microtubule. You could have more than one, of course, up to n. So you could have multiple motors attached, something like this. This would correspond to a state of 4 attached motors. So you can have some m attached motors. So m attached motors, where this m is can go all the way up to n, right? Correct. And when none of these motors are attached to the filament, then the cargo is unbound. So essentially, if the cargo is unbound, if none of this is bound, then the idea is that this cargo can then drift off by 3D diffusion or whatever. So it would no longer be attached to the filament. So essentially, if I am asking a question like this, that how long does this cargo stay bound? The initial state is, of course, the cargo gets bound whenever any one of these motors gets bound. Then motors can bind, more motors can bind, unbind, bind, unbind, whatever. But ultimately, at the end of the day, whenever again I come back to a state where I have one motor and then that final motor also detaches, the cargo becomes unbound, right? So that is my unbound state. What else did I have? I had some binding rates and unbinding rates. So I had a binding rate pi n, right? The range of so these are just for the bound state. The unbound state is m equal to 0, of course. So m equal to 0 means the cargo is unbound. That is the state that I want to calculate the time to. So when I'm saying how long does it stay bound, that m equal to 0 state is my absorbing state, because once I reach that state, that is I want to find that time. So this is the cargo unbound. Okay. All right. So what did I have? I had these rates. So pi n was my attachment rate. So this was my attachment rate when I had n motors bound, attachment rate. With n motors bound. And I had my detachment rate. And these rates were functions. So essentially, if you remember this forward equation that I had asked you to write, those were in terms of these probabilities. That what is the probability that I have n attached motors at some time t, right? And then we had written that, let me see. So if I was writing down, it's always good to write down the forward equation, del p n del t. So here this variable, this variable n. So unlike in, for example, in this protein diffusion case, or a random walk in space case, where what you're changing is your position variable, right? What base of the DNA were you at? Here, this variable that is changing is a state variable, in that how many motors is bound. So you're doing this random walk not on position space, but on state space of the number of motors that is bound. So it's just keep that in mind. So here, if I have this dPn dt, what is the probability of having n bound motors? I could of course come from that state, the gain terms, from the n minus 1 state or the n plus 1 state, right. So, these would be my gain terms. If I were in the n minus 1 state, I would need to attach one motor, and that attachment rate would be pi n minus 1, right. If I were in the n plus 1 state, I would need to detach a motor, and that detachment rate would be epsilon n plus 1. And then of course, there would be the loss terms, the forward. The loss terms would just be minus epsilon n plus pi n. Right. So, this was the basic master equation that we have written down, that you had written down essentially. And these rates being functions of the state makes sense, because essentially if you have for example, this transition of this state where you have n motors bound and you want to go to the n minus 1 through a detachment, any one of these n motors could detach, and therefore, if you remember, not that it's important, but in this until we were solving, but this was just n times the single motor detachment rate. So, if you had n motors bound, it was n times epsilon. Similarly, if you were attaching and nothing was attached, then you would have one rate. If since you have an upper cap, capital N, and then some base rate, which are called, these people are called by AD. But anyway, these rates, attachments and detachment rates, were state specific, in that it depended on what rate, what state you were in. And then you had done various things, but what I wanted today look at is these times, that how long does this cargo stay bound. So, essentially what I want to ask is this mean time, and I'll just talk about mean times for this, not the full. So, here we worked out the full distribution. Okay. So, in this particular case, I'll just talk about the mean time. It's a slightly different approach, but it's an approach which is we have also used, and like we have done earlier, but is often done when you cannot solve the full thing. You just talk about the means, right? So, this mean time to unbind, that is what I want to find, right? Mean time to unbind. Mean time to unbind, starting from M bound motors. And again, this unbind means that you want to reach the M equal to 0 state, because then you have no bound motors. So, that is your observing state. So, I will write this mean time tau M, right, and I will write this recursion relation. Remember, for the random walk also, when we were deriving this equation for first passage times, we started off with this recursion relation, right. So, when we are doing this random walk, from where we did del 2 tau del x naught square equal to minus 1 by d. Remember, we had written down a recursion relation that your time from position x naught was something, how long did you stay over here in one site, plus what could you have done from that site in this initial time step, which is you were starting from x naught. So, you could have gone to x naught plus delta, and then the time from that position, and you could have gone to x naught minus delta, and then the time from that position, and you could have gone to either of these states if this was a symmetric random walk with a probability half-half, right. You remember this? So, that is the approach that I will take. I will try to, instead of doing this full backward formalism, I will try to write down a recursion relation for these mean times starting from this mth state. Okay. Which one? Yes, the rate. These forms of the rates. This is an assumption, of course. The fact that you will have some rate, and that the fact that the rate is going to be dependent on the state variable is not. That's a sort of truth. Whether it is of this form or not, yes, of course, it's an assumption. But again, so I am not going to be explicitly using these forms for the time being. Whatever it is, I will just write in terms of pi n and epsilon n, and then one can do whatever is the correct one thinks rate should be. One can substitute that into these expressions, find out. All right. So I have started from this state where I have m bound motors, and to what states can I go to from this state? Let us not think about the boundary cases for the time being, but if I am in bulk, then what states can I go to? M plus 1 and m minus 1, right. So I can either detach a motor and go to m minus 1, or I can attach a motor and I can go to m plus 1. So I'll have something over here, I'll have something over here, but then I'll have a recursion relation in terms of m minus 1 tau m minus 1. So if you unbind, I'll just keep this for the time being, and then I'll have something over here, and if you bind the motor, you will have the tau m plus 1, the first passage time from site m, m minus 1 and m plus 1. Okay. Right. So now the question is that what will be these prefactors, right? So what will be these prefactors? So let us say I am at state m, so I am at state m. I can go to this m plus 1 state, which is an attachment. So therefore, I can go to this state with the rate pi m, or I can detach and go to the m minus 1 state, and here my rate is epsilon m. Right. So these are my two possibilities, which m minus 1 m plus 1. So if I therefore, I say that these are my two possible processes, and therefore I ask that therefore typically how long would I stay in this state? How long would I stay in this state, given that I have these rates for these two possible transitions? Anyone? 1 minus, who was saying? Sorry, 1 minus epsilon plus you want epsilon m minus 1, but something of this sort you are saying, but you are not sure whether it is m or m plus 1. Okay, someone else? Ratan? Why? Achha, firstly, where did I write? What is the unit of a rate? Inverse time, right? How frequently does a process happen per unit of time? So if you have rates over here in the numerator, the units are inverse time, right? Whereas what you want is something of time. So this definitely cannot be true. Okay. What can be true? All right. So forget about this. I have one process m. It goes to m plus 1 with a rate pi. Right. There's just this thing. What does it mean about the typical time scale of this process? How long does this time process typically? 1 by pi. So that's the typical time scale of this process, right? Now everybody is clear on that, right? Now I have this process where I'm only looking at escape from this state, and that has a cumulative rate of epsilon m plus pi m, because I can escape in both of these ways. So therefore, what is the typical time it will stay in this state before it escapes? 1 by epsilon plus pi. Thank you very much. So you have this transition from m to m plus 1 with a rate pi m. So if this is 3 per second, let us say, you will have 3 such binding events per second, which means that it would stay in this, if I forget for this for the time being, it would typically stay in this state before another motor got bound for 0.33 seconds, essentially, right? That is what this is saying. Yes. No, because I am asking what is the first passage time from starting from this state M. So, from this state M, I can go to two states. I can, because again remember, so what is the idea that I have started from this M? I have to consider the first step that takes me out of this initial state. That is my backward formalism, right? And the two steps are M minus 1 and M plus 1. And what are the rates? The rates are pi M and epsilon M, and therefore. Okay, is that clear? Okay, so good. You have a time scale. So you sum over all the rates. If there were more processes that could happen, you sum over all the rates. The typical time, residence time in this state before it escapes through any one of the available pathways would be the inverse of the sum of the rates. Now, what comes here? What comes here is the probability that I go to this state, and here comes the probability that I go to this state. Okay. What are these probabilities? Very good. So, which one is epsilon M is the unbinding. Right. And here the probability is pi M by epsilon M plus. Okay. So, you have these two processes with these rates. The probability that you choose this process is proportional to that rate, of course. If you have a higher rate for that process, you'll have a higher probability. The probability that you choose the other process is proportional to that rate. These are the only two processes that can happen. Therefore, the sum of these two probabilities must add up to 1. Therefore, this is epsilon M by epsilon M plus pi M. This pi M by epsilon M plus pi M. And this is exactly what we did here. So, this half would have been U by U plus U, because your two steps would have been U in both directions. In one direction, it would have been U, and again. So, therefore, this half is actually U by U plus U. This tau would be 1 by 2U, right? What would be the typical residence time? So, I want to know that what is the probability of this process M going to M minus 1, and what is the probability of this process M going to M plus 1, right? Now, these probabilities would be proportional to the rates of these processes, right? Higher the rate of one process, the higher the probability that you would go to that. So, let me call this alpha times this was what? Detachment. So, epsilon M, beta times pi M, right? The sum of these two probabilities have to be 1, of course, because you either have to do this or you have to do that. You either, I mean, once you're escaping out from this state, you either have to attach or you have to detach. Those are your only two options. So, therefore, alpha epsilon M plus beta pi M is equal to 1, right? Yes, but I mean that you're thinking when we were only doing this one step, like you had only one option, right? But now you have these two processes, and you have to ask that what is the probability of this process as compared to that, and that's how we will get the rate. So, but essentially, let me see. So, you can still think in terms of that perspective. So, except that your delta t now, the time that you take is essentially good M plus pi M, because that is the typical time that you take to escape out of this state. So, the probability into this delta t is what is going to give you the rate, and therefore, you will get this terms, right. So, in general, if you are just interested in the mean times for these processes and not in the full distribution of times, you can of course get these mean times like we did from the Fn tildes like we did in the previous example. But often it is easier if you're just interested in the mean times, you can often write down this recursion, this sort of a recursion relation, and these recursion relations are often more easier to solve. Of course, I should write down the boundary conditions, which is that if you are starting from n bound motors, then you cannot attach anything else. You can only detach, which means that you only have 1 by epsilon n plus average tau n minus 1, right, with probability 1 essentially, because that's the only possible step. This is akin to a reflecting boundary condition at n. The other is, of course, that you have this absorbing state at 0. So if you have started with, once you reach the 0 bound motors, that time is 0. So that gives you a full set of equations, and you can then solve this. Again, I'll just write down the solution, because ultimately, if you are actually looking to the mean time to unwind for a bound motor, then that means essentially what you are looking at is the starting state m equal to 1, because whenever you have one bound motor, your motor is bound. And in that particular case, you can write down the solution. Again, just write this down. If you cannot solve it from this system of equations, you let me know and I will tell you. Okay. Again, you can go to this paper and take a look as well. All right, so I'll stop here.